Welcome to the class on describing functions of nonlinear elements. With this topic, we jump from issues related to discrete systems to issues related to nonlinear systems. In today's classes, we will determine a describing function. That is, we will perform a kind of linearization using the describing function method. This method makes two assumptions: that the input signal E of t is sinusoidal, and that the linear part of the system has the properties of a low-pass filter. That is, there is an inertial object behind this nonlinear element in the system. The describing function consists of two equations that are presented on the slide. One equation is for the transient component and the other for the steady-state component. The values a and a0 should be treated as known because they are parameters of the input signal. Therefore, only the components b0, b1 and c1 need to be calculated. The following slides will present formulas for the components b0, b1 and c1, but also their partial derivation will be shown. B0 component is the integral on interval from 0 to 2p of some function dependent on the input signal with respect to omega t, and this is divided by 2p. But this input signal can be written directly as a sine. The formula for B1 component is almost the same as for B0 component. The only difference is the coefficient before the integral and the fact that the integral is calculated from the same function but multiplied by the sine. The product of angular velocity and time can be replaced by angle phi. And the last component c1 differs from the component b1 only in that the function in the integral is multiplied by cosine, not by sine. This function, from which the integral will have to be calculated each time, is related to the so-called static characteristic of the nonlinear element, and is different for each nonlinear object. The result of passing a sinusoidal signal through this function is denoted by u of phi. And finally, we will use such formulas in today's classes, and the determination of the u of phi signal will be carried out graphically. On this slide, I present examples of static characteristics u of e. The third characteristic has hysteresis, whereas the last of the static characteristics is the characteristic of a linear object, specifically a proportional object with a gain equal to tangent of alpha. In the formulas shown earlier, it is necessary to calculate the integral of the function u of phi. This is the function on the right, and it is for the static characteristic presented in the upper left corner. The sign at the bottom represents a sine function passing through a nonlinear element. There may be two special cases that reduce the calculation of the describing function. If the static characteristic is symmetrical, then a0 and b0 are equal to 0. Moreover, the steady-state component of the describing function, j0, doesn't exist, and the transient component depends only on the variable a, so we write j of a. But symmetry, which we mean here, is with respect to a point, and specifically with respect to the origin of the coordinate system. The second special case occurs if the static characteristic is single-valued, that is, if there is no hysteresis. In this situation, there is no need to calculate the C1 component, because it is 0. The next three slides describe how to determine the function u of phi. I won't go into much detail about it now, because it's much easier to understand with specific examples. However, please remember that the result should only contain variables from the task content. If an additional variable is introduced for convenience, it should be expressed at the end using the symbols given in the task content. In certain situations, the performed calculations can be accelerated. The interval of integral doesn't have to be exactly from 0 to 2p, it just needs to cover one full period. Furthermore, if calculations are performed for symmetrical static characteristics, these calculations can be limited to a quarter or half period. 1/4 of the period is sufficient for characteristics without hysteresis, and half for characteristics with hysteresis. However, it should be remembered that the correct result is 4 and 2 times greater, respectively. One can also use both of these accelerations at the same time, that is, calculate the integral of a part of the period, and this part of the period doesn't have to start at 0. So, let's move on to some examples. By the way, I would like to remind you that this is a topic on which you have access to the entire set of tasks that I have prepared so far. Therefore, tasks from this list will definitely appear at the test. The first task is calculate the describing function of nonlinear element with the given static characteristic. We start solving by drawing a sign that passes through this nonlinear element. The axis designations can be either e of t and then omega t should be written on the second axis, or this sign can be designated as e of phi and then phi should be written on the second axis. The sign can be of two types. It will either start from the origin of the coordinate system or from the value a0. If the static characteristic is symmetrical, and that is what we are dealing with here, then a0 is equal to 0. Then we need to mark the angles at which switches or breaks in the static characteristic occur. In this case, it is just p. Now we need to draw a graph u of phi. Also, on this graph, we are drawing for the range from 0 to 2p, and for each angle at the sign e of t, we look at what value u this sign is put on. For example, for this angle, the value of the sign is this, and this value is placed on the characteristic here. Therefore, for this angle, the same as here, u of phi is equal to large u. And we need to do exactly the same thing for the entire period of the sign. After a while, you should notice that for each angle in the first half of the period, the sign is positive, so it will put on value large u, and for the second half of the period, the sign has negative values, so the function u of phi will be equal to minus large u. Once the u of phi function is ready, we can start calculating all the necessary components. B0 component is equal to 0, because the static characteristic is symmetric. Moreover, the static characteristic has no hysteresis, so C1 component is also 0. We only need to calculate B1 component. Each time we will divide the integral into fragments, in which the function u of phi has the same formula. Large u is a constant, so one can take it in front of the integral and then in front of the bracket. The integral of sine is minus cosine. We subtract the lower one from the upper limit. I always recommend drawing an auxiliary chart somewhere on the side to avoid making mistakes. We now have everything we need to write a describing function. Let me remind you that since the static characteristic is symmetric, the describing function is limited only to j of a. And this is the solution. But let's try to calculate b1 again. This time we will use only 1/4 of the period. So we see that we got exactly the same result. And what would happen if we forgot that the components b0 and c1 are equal to 0? If we make no mistake, we will get correct results, but only when calculating over the entire sine period. In the case of calculations for a quarter of a period, the obtained result will be incorrect. We can see that it can be calculated normally, but then we lose valuable time, which will not be enough for the test anyway. I also wanted to show you an animation that may help you understand how a graph u of phi is created. The static characteristic is symmetric, so the sign starts at the origin of the coordinate system. The angle changing in the graph at the bottom is the same angle we see in the graph on the right, and we look at the value of the sign for each angle. These values should be put on the static characteristic. Moreover, if we are dealing with hysteresis, we should be careful at what angles the switching occurs, always according to the arrow on the hysteresis. And these values from the static characteristic should be plotted on the u of phi graph. I hope this was helpful. In the next task, we will calculate a describing function for such case. The static characteristic is not symmetrical, so a0 is not equal to 0, so the drawn sign must have a constant component. If someone wants, the beginning of the sign can be at a negative value, but even then this point should be marked with A0, not minus A0. The amplitude of the sign should always be large enough to cover all interesting points on the static characteristic, that is, all switches and breaks. Now we need to mark the angles where these switches or breaks occur. In our case, these are these two angles. Here we will introduce an auxiliary variable phi1, and regardless of how many auxiliary variables we introduce, each phi must always be an acute angle. Therefore, when writing these angles, we will use p and 2p. Now we need to draw the effect of this sign passing through the static characteristic. Only this time we are not dealing with a horizontal fragment. Let's look where the u of phi characteristic starts from. Similarly for some small angle. And now for the angle 1/2 p. This seems quite complicated, but imagine what it would look like if angle alpha was exactly 45 degrees. The value of A0 on the e-axis would correspond to the value of A0 on the u-axis, and the same with every other value. This means the chart would be simply redrawn. So, what changes if the alpha angle is smaller or larger than 45 degrees? The signal will simply be rescaled. Specifically, it will be scaled by the alpha tangent. So we need to draw the sign on the graph u of phi. This would be a full sign if we had a linear object, that is, if the entire characteristic was inclined at the same alpha angle. But our nonlinear object takes the zero value for sign less than 0. So in the range of angles from p plus phi1 to 2p minus phi1, the function u of phi is 0. So let's move on to calculating the b0 component. And this is where the problem arises. What is the actual value of the function u of v in this interval? We have actually already said that this is the same sign as in the input, only it is scaled by the alpha tangent. To this, we need to add the second integral at the end of the period. We ignore the segment equal to 0 because the integral of 0 is 0. The alpha tangent is a constant, so we can take this out before the integral. And the integral of the sum can be converted into the sum of integrals. A and a0 are constants, so we can take them out before the integral. And this is where trigonometric reflections and shifts formulas would come in handy. Do any of you remember them? Me neither. Therefore, I recommend drawing this function somewhere on the side and deriving these trigonometric reflections and shifts formulas based on it. The cosine of p plus the small angle is equal to the cosine of the small angle but with the opposite sign. Whereas the cosine of 2p minus the small angle is equal to the cosine of the small angle. However, we cannot leave this variable phi1 in the result because we introduced this variable ourselves. To calculate what is equal to phi, we should use the sine graph and choose any angle containing phi that we want to determine. We have a choice between p plus phi1 and 2p minus phi1. In both cases, our sine of this angle is 0. Regardless of which angle we choose, we will get the same formula. This time we need trigonometric reflections and shifts formulas for the sine. So again, we draw this function and determine these formulas graphically. And we substitute this formula for phi1. But in the case of cosine, we use a different formula. It's known that we take the cosine from this. And what is the sine of phi1? We just wrote this. Hence, and based on this component, we can determine the describing function for steady-state component. 2 are cosinus. Before we proceed to the calculation of B1 component, I would like to draw your attention to the possibility of speeding up the calculations. We can draw a fragment of the U chart on the left. The integral must be calculated over one period, but this period may start from minus phi1. Well, we see that we managed to obtain the same result. So, let's move on to calculating B1. We have the integral of the square of the sine. But please don't worry, I don't require memorizing the formula. If you need to use it, this formula will be provided in the task. Well, I usually stop this task at this point because I run out of time at the end of the class, but usually the recordings were shorter, so I will complete this task. Still, based on this nonlinear element, I would like to discuss one variation of tasks that may arise. The components should not be calculated in them, but the formulas of the function u of phi for subsequent intervals should be written. After solving the previous task, I assume that there will be no major problems with completing this one. If there are too many spaces to fill, we leave the rest. And if there are not enough spaces to fill, you should write entire lines manually, as many as needed. And in the content of such tasks, there may be either information that the markings phi I can be left, or there will be an instruction to determine the formulas for all phi I. In our case, there is only phi 1 to determine. Now let's move on to the nonlinear element with hysteresis. The static characteristic is symmetric, so I draw the sign from the origin of the coordinate system. But the sign must have a large enough amplitude to cover the points of interest on the static characteristic. In other words, big A must be greater than small a. Due to the fact that the static characteristic is symmetrical, we could also use phi 1 for the third and fourth angles. Which value will we start drawing a graph u of phi from? From minus u or from plus u? We will start drawing from minus u, because the function u of phi is a periodic function. So we need to look where we will be after the previous sign period and start drawing from there. For angle phi1, the value is switched to large U. However, the return will not occur for the angle p minus phi1, because we have hysteresis, and this switching was only possible in this direction. Switching to large U will only occur for the angle p plus phi1. Well, until 2p we will remain at the value of minus large U. The static characteristic is symmetric, so b0 is equal to 0. We need to calculate the components b1 and c1. I will speed up the calculations by shifting the interval. And we will determine the value of cosine phi1 from the Pythagorean trigonometric identity and from the sine graph. For the angle equal to phi1, sine is equal to exactly small a. In the calculations, we used a range shift to have fewer integrals to calculate, but for symmetric static characteristics, we can also shorten the interval. Here we are dealing with a nonlinear element with hysteresis, and in such cases we can perform calculations for half of the period. I will now calculate the same component, but also using this second calculation acceleration. We see that we obtained the same result, but the calculations were shorter. Let's now proceed to the calculation of the C1 component. Therefore, the describing function of this nonlinear element is This concludes today's classes. I highly encourage you to practice solving tasks on this topic. However, it will make the most sense to start with 3 such tasks. If you manage to solve these 3 specific cases, where the third one is a combination of the first 2, it will be much easier for you to solve the set of tasks that I have shared with you. And that's all I wanted to show you during these classes. Thank you very much for your attention and have a nice day.